All right, so this here is another example, adding and subtraction of phasors, right? So then we are looking at this junction right here, right? We have I1, I2, I3, I4. If this were to be, and then this, we've simplified just that junction to see this, right? So this is not the phasor as we've written here, not the phasor diagram. It's just simplifying of this junction here, sorry, this node here to see what's actually, to make it clearer, right? So if this were to be AC, we'd have just added the values for I1, I2, I3, and I4. Sorry, I1, I2, I3, just to get I4, right? Or add any other one to do algebra to get the other one, right? To find what we need. But then again, this is DC. Sorry, this is AC circuit, alternating current, right? So then there's a quantity we have for I1, I2, I3, and then as we're looking at how everything is configured here, because I goes in, I1 goes in, I2 in, I3 to the node, I4 is the only one from the node, right? So then we are trying to find I4, right? When it comes to addition of phasors, right, we can only add quantities that have the same frequency, right? We can only add the ones with the same frequency. So if you look at this very well, if you're able to spot this out, or if you are familiar with what we've been doing so far, you'll be able to find out the ones with a similar frequency, right? So let's see. Let's go through this. Clearly, these ones here are just the, what's the name? The phase shift, right? Or the phase angle, right? So that's not how we check whether some quantities are in phase or not, right? So sorry, whether they are having the same frequency. So this is how we check it. We said this W here, this angular frequency. So we have 2 pi f, right? So then this is what the frequency is. So basically we look at this side, this side, this side, this side, right? This. So clearly these are the ones that have the same frequency. That's why we have the W and then the T, W and then the T. That's alone, nothing else attached, right? So we'll be looking at these ones together, and then we add them, those ones together. This way we add them, and then we move on to find this, and then we put everything together. For these ones who having the same frequency, right? 30WT, 30WT here. This is just the phase shift, right? Okay. So previously the one with the quantities were 90 degrees away from each other, so it was a bit straightforward. But here's the case that they are not close to each other. The what do you call it? The phase difference is not 90, right? So we have to find a way. So that's how we go about it. So we look at this one, for instance, the first one. So now we are dealing with the one would have the frequency of just WT. So let's see. WT frequency. Write this one. Frequency. Right? So which is this one right here. So this is how we go about it. So from the first example, we saw that they were 90 degrees apart. But looking at this one is in line with the x-axis. This one is not 90. This one is not 90, right? So we can add them up straight forward as we were doing previously. So this is how we go for this one. To do that, let's just try and simplify this whole thing. So the 5 is about here, right? There's the 5 sine WT, right? And then the second one, I2, that side of the I2, this side of the I2 is leading, right? So be about here. So this be the 8 sine WT plus pi on 3. And then this side of the I3 is lagging. It's lagging by this small one here. We know it's negative, so lagging, right? So that's 15. We have sine. We have WT. So let's put this in brackets. And then we have a minus pi on 4. So this is what we have. All right. So before we do this, for this particular, because they are not 90 degrees away from each other, we find a way. We get their x part, what we call x component, and then we get their y component as well. And with this, we move on to help us find the phase shift and everything. Similar procedure to the previous one, but slight difference. Okay, so this is how I go about it. So now we are trying to find the s component. Okay, so looking at this one very well, this sign here, this one is in line with the x-axis, so that one is straightforward. So if we are trying to find the s component and y component, so now we are trying to find the s component. Right. Okay. So this one right here, the 5 is in line with the x-axis, right? So it's just the 5, just the length. So basically, we are looking for the length, which is kind of like the RMS, right? We're looking for it, which is like the RMS. So as we said, the faces, their length represent the RMS value, right? Yeah. And then the direction tells us relative to the x-axis, right? So because this one is 5 here, right? And then it's 5 here, right? Let's see. This one is 5 here, right? That's the RMS, right? And it's in line with the x-axis. So that's actual 5. That's the actual RMS for that one, right? Okay. And then for this one, you have to get the RMS, which is the actual length. You have to get it horizontal, right? Or parallel to the x-axis. So that's how we do it. And we see 8, right? And we do a cos, and then you get angle from this, which is basically pi on 3, right? And this pi on 3 is the same as because we know pi is equal to 180, right? Pi on 3 is about 60, right? About 60 degrees to be more specific. 60 degrees. So that's 60 degrees. And then what do we have? 15, right? 15. You want the s part, so that's cos, right? That's 180 on 4, and that gives us 45 degrees. So let's do this. So basically what we are doing now is just like a build up of what we've been doing so far. Just a build up. So if you understand the one that they are 90 degrees away from the other, you understand this one clear, like relatively easier. Because you know that they are not 90 degrees away from each other. So we find a way to get their actual RMS, right? But then we find the angle. Okay. So now this. So that's cos. Let's see. Whenever you're dealing with this pi stuff, you're dealing with trigonometry, right? You have to be very careful. We know pi is 180, so we just do this 180 on 4, like it's at 45. If you choose to use radians, then you have to do it in radians, right? But if you choose to do it in degrees, you have to make sure your calculator is working in degrees. Cos 45 degrees. Okay. Alright, so this will give us, let's see, 5 plus 8 cos 60 plus 15 cos 45, and this is giving us 19.36066 degrees. And now we are looking for the y component for these ones. So you see, then again, we are still at the moment we are still adding these ones, this, and this. Why? Because they have the same watt frequency. So we are just working on this. Right. So basically, in the end, we end up getting something that looks like a summation of other different ones. So now we go to the y component. Right? Y component. And looking at this, the Phasor right here, if you want the y component, meaning you have to trace this to this, trace this to this, right? And this x here is still, so there's the y-axis, this x-axis, right? So and this 5 1 here will just be here, which will be 0 here, right? So clearly, we know that for the 5 1, the s component, so the y component is 0, right? And then for this a here, the y component is 8, right? Sine 60, right, degrees. And then what do we have? Let's pay attention to this. You see, for the x side, we have plus, right? See this one right here. So let's do this. So when we draw the coordinate system, right, the Cartesian, we have x here positive, we have negative x here, right? And we have positive y here, and we have negative y here, right? Very clear. That's why when we are doing this one, when we find the s component of the 8 is here, still positive, right? When you find the x component of the 15, it's still your positive. This one's positive. That's why it's plus plus plus. But when it comes to the y component, right? Okay, the x is 0, so this 15 here is 0, right? This 8 here, okay, for this 8 here, it's still up here, so that's positive, right? But for this 15 here, right, it's below, so now it comes to this side, right? So let's draw this again. So x positive, x negative, this y positive, y negative, right? So this 15 here traces to this side, this origin, there, so the origin is here. But then this 15 traces to this side, so negative. So that's why here we get minus. So I'm coming at the sine, and we have a sine here. Okay, and this is 0. This is minus. Okay. All right. So this is 0. This is sine plus, right? And for the 15 one, it's negative. So that's 15 or sine 45, right? 45. Oh, 45, right? So that gives us a minus 3.678 for approximately 4 dB, right? So we have these. So this is what will help us to actually get. So basically, this one gives us the magnitude. Let's see. Now to find the magnitude of the resultant of these three, when we like do the algebraic sum, this is what we do. Just like how we did it for the ones that are 90 degrees apart. So basically, to get the RMS, so the peak value for that one is this way. We just do square root. So instead of that one, what we do it directly, because they're 90 degrees apart, this one, we find the x and y component and use it to get that one, right? So let's see. So this, we use this 19 point, this one right here. This. That's the x component, right? So 19.6066 squared, and then we'll do a plus, and then we'll do a minus, not just minus, this value right here. Right? So that's minus 3.6784 squared as well. Squared as well. So square root is for all of them. Okay, so let's see what this gives us. That's 19.60666 squared, and I have plus. When it comes to negative, it's safe to put it in brackets, so it's easier to compute. Squared. Then we have 3.6784, and that gives us the peak value for the summation of these three to be 19.9487 approximately for the peak. So now we have this. The next one will be to find the, what do you call it, the phase shift relative to what the x-axis, right? Yeah, so that one we'll still use this once again. Yeah, we'll still use this once again. So let's see. So we still be using tan. We know tan theta is equal to opposite of adjacent, right? Opposite of adjacent. All right, and then if we are doing that, mean basically we are opposite to be the y-axis, y, and adjacent to be the x. So adjacent, opposite is y. And we know this one here is the y, this one is the x. So there's the x, there's the y. So now to find theta, theta is equal to tan inverse of opposite, which is a y. We have that to be minus 3.6784, right? And then the x to be 19.6066, 19.6066. Let's for these ones you bring in the negative, right? You have to bring in the negative when you are computing the phase shift, right? The phase shift. Let's see. So tan inverse. We have minus 3.6784. We have 19.6066. So that gives us, so this one gives you clearly the direction, right? So whether it's leading or lagging. So it's giving you minus 10.62. It's giving us, yeah, 7 degrees, right? So this basically shows it directly. So instead of what we saw in the first example, that one you have to check and see. But this one gives you straightforward, especially when you put in the signs and everything, whether it's leading or lagging. Right. So now we have this. So for the W frequency side, for the W, the frequency where the frequency is W, right? This we'll end up having, where's the magnitude, right? So there's the peak, as we said. So for AC quantities, basically we have the peak, and then because when it's a sine wave, right? So this for AC quantity sine waves. So peak, sine, and then we have a frequency, right? If it's not a change or something. So here could be a value or something. So this here could be 1 or anything. So let's try this one. So we have peak, sine wave, which is a sine wave, right? Sine, and then we have this. Let's say we have W, we have T, and plus or minus theta, right? Where it's an integer, right? What do you call it? Positive integer. Positive integer, right? Yeah, and this could be anything, whether it could even be 0, right? So now we have the peak. The peak is 90.9487. So now we are talking about the one with the frequency being just this, right? So we have 19 points. So this is the peak. 9784. 9487. Sorry. 9487, right? And then sine, right? And this one right here, this hour here is 1, right? So because we're adding the ones that have a frequency of this, right? So 1, and then angular frequency T, right? And we have the phase shift here, which is this minus. So minus 10.6. Let's make it this way. Minus 10 points about 6.2 degrees. Yeah. So now we are done in the part of I4, right? The part of I4 that has a frequency of just WT, so just ones. So we are done adding these ones up. So now we are going to move on to this side, right? Same procedure, but just that the frequencies are different, so we add them separately. Okay, so now we are dealing with the 3 WT frequency. Okay. So we're adding these ones up. So as we said, each what do you call it? Sinusoidal quantity has its own way of representing it. So the general one is we have the peak value, right? And then because they are sine functions, we have the sine, and then we have the frequency aspect, and then we have the phase shift. So if there's no phase shift or there's no phase angle, meaning it's in phase with the normal sine function where it starts from the origin. So now you're going to do this. So now you're going to find the x components, right? Alright. So to do that, so let's see if we can make a small representation here. just to solidify our understanding of what we are doing. So in actual sense, if you have to draw the faces for this is just a freehand sketch. For this particular side, for the 5, this particular side, what do you think? Because there's no face angle, to end up being in line with the x-axis, right? So the face will be straight, so to be like this, right? Because this way of representing it here just tells the RMS value by the length, right? And then the direction, and then the angle to the x-axis tells us just the face difference, right? Let's see. So if there's some axis here, right? This will be the 5. So this is the 5 sine AWT. It doesn't tell us the frequency though. And then the 8, so you see it lags because of the negative here, so it should be somewhere about here. Then again, this freehand, but then we've seen so far that the first values here, this, and then this are their peak quantity. So in natural terms, the one for the 8 will be longer. Right? You have to draw it to scale. Right? This will be the 8 sine the AWT minus pi on 3. Right? Oh, shoot here. This is 3. This is pi. Okay. So now we are trying to look for those components, right? Clearly, if you are trying to get, it can get to a point that when you understand it, you even have to skip drawing the diagram, so you can go straight forward. So clearly, for these components of this one right here, it's just the 5, right? So that'll give us 5 plus that of this one, so we get 8. We have a cos, right? And then this 180 on 3, right? And that gives us 60, right? 60 degrees, right? That's this component, so let's see what it gives us. Then again, if you try to understand 1 or 2 examples, the rest become easier to understand. Just have to know the general formula, know a bit of rearrangement of the values, and then yeah. So we have 5 plus. Then again, we are doing this in degrees, so make sure your unit here, calculators can operate in degrees or radians. So degrees here, so here should be in degrees. So see whether degrees or radians. Yeah, so we are doing degrees. So 5. That unit there is very important. 5 8 cos 60, right? And that gives us 9. Okay, now y component. Let's see. We have let's go back to the diagram. We just use the diagram just to make sure it's clear. Because this one is actually in line with the x-axis, you try to find the y component to just be here. That's 0. Right? We have 0 plus 8 sine 60, right? 60 degrees. So there is an overside that we must correct. So we are seeing here as positive, right? Because we are expecting negatives there, right? But there's the reason. In the actual question, we changed something. So that's why it happened that way. So my mind was still thinking this positive. So in actual sense, the original question that we're actually working on here is positive. Here is positive. This side is positive, right? So it leads. So let's see. So that's the 3W frequency aspect. So all these are now affected. Then here. So this as well. So this is the side that's affected. So in actual sense, this right here is what is affected, right? Okay. So this is what is affected. And then this one moves here, right? And then we have this, right? And then this is positive, right? So this is positive. So it's leading, right? So it's leading. So here S positive, leading. Let's see. Some of them must correct. Corrected the very first one. So yeah, so it's leading. Third of you is leading. So that's why here is positive and not, so here is positive here. So that's why in this actual one is positive. Alright. So that's 8 sine 60. That gives us this. So we have 6.92. Let's do 4 dB. 82. Alright. So now that we have these, then again, we said the x and y component help us to get what's the name? The actual. So let's go over this. We said the sinusoidal quantity has a Vm, has a peak value, and because they are sine functions, or sine with sine, right? And then we have this one right here, which could be any number because of the frequency. We have the angular frequency, we have time, and then we have phase shift, plus or minus, depending on the angle, right? And then we are saying that because they are more than one, we try and, if you are trying to find the resultant, we find the Vm, right? Which is what we've done so far. Now we're trying to get the Vm, and then we get this phase shift here, right? Okay. So now we found the x and y component. That same one help us find our Vm, and the same thing help us find our Vm, right? And help us find the phase angle, right? So now we found the x and y component. So trying to find the Vm, this is how to be. So let's see. Go over this once in a while just to make sure we are clear on what we are doing. The Vm that we are looking for, we square root of 9 squared plus 6.9282 squared. And then it's very important that if you get values negative, make sure you put it in bracket so that it's easier to compute and then less confusing. Right, so let's see what we have over here. So you have square root 9 squared 6.9282 squared. Yeah, and that gives us 11.3578 dp. Right. So now we need the phase angle. So then when you go to diagram again, we know that the what you call the 5 1 is here, and then the 8 is here. So that means that we'll get a triangle of this sort, something like this. This. You get to a point that you don't even have to draw it, you just know, because this is negative, this has this lagging, this is in line, so it will have a triangle like this, right? So if you're trying to find the theta or the phase angle, that's tan inverse. Usually tan is theta is opposite over adjacent, right? So that if the phase angle will be here, and the opposite that we're looking for is this, right? And that's basically the y. And we know the y component is this 6.9282 point, right? And then the x component is just 9. So that's what we are getting. 6.9282, right? Now we have a 9 here. Then again, unit very important because we are dealing in degrees. This should be in degrees. That's 37.5891. That's 4 dp. 4 dp. So now we have the peak. Then again, representing sinusoidal quantities as a function of time, right? So we have the maximum, we have the sine because they are sine functions, and then we have the frequency. Here could be any value, right? Angular frequency. Oh, this is the frequency, just a portion of frequency. And then we have angular frequency, we have time, plus or minus, and then we have the phase angle, right? So we found the peak. So basically what we're writing right now is the, what's the name? The 3WT part of I4, right? So we know the peak. The peak is 1135 11. So let's write it out. So we have 11.3578. Right, now it's a sine function, so that doesn't change. And then there's the part we said, there's the 3 wt part, so 3 wt, right? And then most of the times, whether there's a plus or minus for this particular one, where they are not in 90 degrees to each other, you just use the value, whether positive or negative, to tell. So this one is just positive here, right? There's no negative, so that's a plus. So that'll be plus 37 point. Let's make this small. A minute. So yeah, it's basically the same process, because they are different frequencies. That's why we add them up differently. 7, 5, 8, 9, 1. Yeah, so this is it. So if we are to write the full representation of the I4 minutes, we add all the, what do you call it, for different frequencies, we add them up. So this one right here is for just the WT frequency part, and we just add it up to this one. So basically the full I4, so full I4, that's the there's this frequency plus this frequency, everything all together, right? This what gives us, we have this. This is just the W frequency part, and then we have this one, this right here, what we just did. Yeah, so we can clearly see that they are still all following the same format as this right here, right? So we have the peak, they are sine, so we have sine. This is the different frequency from this one. So this and this are different, right? And then we have the phase shift, right? And then we have another, for this one right here, we have this phase shift to be here. So this one here is lag, and this one here is leading. So it's just the same sinusoidal quantity but has different parts. So in actual sense, if we look at this very well, we can generally see that this is kind of like a harmonic, right? The resultant current is a harmonic, right? Because it's composed of what do you call it, part of different frequencies. And to be much more clearer, this one is just having just one here, this one is 3, so we can end up seeing that this is kind of like an odd harmonic. All right, so that's it.